Something is happening to you when music gives you chills that you have almost certainly never examined carefully. Your skin tightens, hairs stand up, there's a catch in the chest, something that feels like it matters, even though you can't say what it is or why. Sometimes tears, not from sadness exactly, not from joy exactly, from something that doesn't have a clean name. And the thing producing this is, physically, oscillating air pressure. Compressions and rarefactions in a gas, moving at 343 meters per second, arriving at your ear. That's it. That's the complete physical description of what music is. Mechanical waves in a medium. Your nervous system, built over millions of years of evolution to detect predators, find food, navigate social threat, is producing a full physiological stress response to organized vibration in air. That gap between what music physically is and what it does to a human body is one of the most interesting unsolved questions in neuroscience. And almost nobody thinks of it as a scientific mystery. They just call it beautiful and move on. I don't want to move on. Start with the physics because it's more interesting than it sounds. Sound is a longitudinal wave, a wave of pressure variation propagating through a medium by compressing and rarefying the molecules in its path. In vacuum, there's no medium, so there's no sound. Music in space is silence. What you call pitch is frequency, how many compression cycles per second. Middle A is 440 cycles per second, 440 hertz. What you call timbre, the quality that lets you distinguish a violin from a piano playing the same note, is the shape of the pressure waveform. A pure sine wave at 440 Hz sounds thin and electronic. A violin at 440 Hz is rich, complex, full of overtones, frequencies at integer multiples of the fundamental, each with its own amplitude, producing a waveform that's mathematically complicated but acoustically distinctive. Musical harmony is built on frequency ratios. An octave is exactly 2 to 1, 440 Hz and 880 Hz. A perfect fifth is approximately 3 to 2. A major third is approximately 5 to 4. When you play two frequencies together, they interact. Their waveforms add together, sometimes reinforcing, sometimes cancelling. For simple integer ratios, the combined waveform is periodic, it repeats cleanly. The auditory system registers clean repetition as consonants, stable, resolved, at rest. For complex ratios, frequencies that don't share simple mathematical relationships, the combined waveform doesn't repeat cleanly. It's irregular, beating, unresolved. The auditory system registers this as dissonance, tension, something unfinished. Music is the deliberate manipulation of tension and resolution through frequency ratios over time. That's the physics. But physics alone doesn't produce goosebumps. Something else is happening. The brain is not a passive receiver of sensory information. That framing is wrong, and replacing it with the correct one changes everything about how you understand music. The brain is a prediction engine. It constantly builds models of what's about to happen, based on past experience, on statistical regularities in the environment, on learned patterns, and uses incoming sensory data not to build experience from scratch, but to update those models. What you perceive is not raw sensation. It's the brain's best current model of what's out there, continuously revised as new data arrives. This applies to music with unusual force, because music is deeply structurally patterned. After a lifetime of exposure to musical conventions, harmonic progressions, rhythmic frameworks, melodic shapes, formal structures, your brain has built an elaborate predictive model of how music moves. You don't consciously know the rules of tonal harmony, but your auditory system has internalized them through exposure. You feel when something is coming. You feel when something resolves. You feel when something is wrong. Musical tension is generated when the brain predicts one thing and the music does something different. Not random different, purposefully, precisely different. A held note that delays resolution, a chord that moves sideways instead of forward, a melody that goes higher than expected. And then resolution, the prediction finally confirmed after the delay. The chill, what researchers call frisson, happens at a very specific structural moment, when the music does something the brain didn't fully expect, but that feels, in retrospect, inevitable. A sudden dynamic drop into silence before a climax. A key change that lifts the melody into a new register. An unexpected instrument entering, a voice cutting through an orchestral texture. A harmonic resolution withheld and then delivered. The chills aren't a response to the sound. They're a response to the violation and resolution of your own expectation. The emotional content is generated inside you by your brain's model of music meeting music that's smarter than the model. In 2011, a neuroscientist named Valerie Salimpour and colleagues at McGill University did something that should have gotten more attention than it did. They used PET scanning to measure dopamine release in people listening to music that gave them chills. And they found it. Real, measurable dopamine release in the striatum, in the nucleus accumbens, the deep reward circuitry of the brain. The same system activated by food when you're hungry, by sex, by addictive drugs. Music activates the dopamine reward system. But here's the part that makes it strange. The dopamine release happened in two places in time. There was a peak at the moment of the emotional chill itself, the expected part. But there was also measurable dopamine release in the caudate nucleus in the seconds before the peak, during the anticipation. The brain was rewarding itself for correctly predicting that something emotionally significant was about to arrive. The brain is not just responding to music, it's rewarding itself for understanding music, for having a good enough model to know that something powerful is coming. This is ancient reward circuitry that evolved to reinforce biologically critical behaviors, being activated by abstract, organized sound. No calories, no reproduction, no survival advantage from the acoustic pattern itself. The biological reward system has extended itself to something that, by any strict evolutionary accounting, it shouldn't care about. Why? That's where it gets genuinely unresolved. Music is universal. Every known human culture has it. Researchers have looked. Specifically, anthropologists have searched for cultures without music and found none. This universality is a signal. Things that appear in every human culture aren't accidents. They're connected to something deep in human cognition or social structure. Several explanations have been proposed for why music exists biologically, and I want to go through them because each one captures something real, and none of them is the whole story. The social bonding hypothesis. Synchronized movement and synchronized vocalization, rhythm, singing together, may have strengthened group cohesion. When people move together to the same beat, it increases feelings of affiliation and trust. Music may have been an early social technology for coordinating large groups who weren't close kin. Strangers moving together, working together, made temporarily into a unit by shared rhythm. The language precursor hypothesis. Music and language share neural architecture in ways that go beyond what you'd expect by chance. Broca's area, long considered a language region, is active during music processing. The auditory cortex, motor systems, syntactic processing regions, they're all recruited by both. The hypothesis is that music and language share evolutionary roots, that musical vocalization may have been a stepping stone toward the complexity of human language. The emotional communication hypothesis. The acoustic features that make music sound emotional, rising pitch signaling excitement, slow tempo signaling sadness, sudden loudness signaling alarm, mirror the acoustic features of emotional human speech and voice. A mother's voice rising in pitch when speaking to an infant, a voice slowing and deepening in grief. Music may be a formalized, extended version of the emotional information already embedded in how humans use their voices. Darwin had his own answer: sexual selection. Music as a fitness display, demonstrating cognitive flexibility, coordination, creativity. Selected for the way peacock tails are selected for. Not because it solves a survival problem, but because it signals the kind of mind that can produce it. Each of these explains something. None explains why the response to music includes a physiological chill, why the autonomic nervous system, the ancient preconscious survival-oriented nervous system, would respond to organized sound patterns with goosebumps. The evolutionary account of frisson specifically remains open. Let me tell you what's actually happening in your body during a chill. The mechanism is specific. Frisson involves piloerection, goosebumps. Tiny muscles called erector pili, attached to hair follicles across your skin, contract. The hairs stand up. This is the same response produced by cold, by fear, by sudden threat. It's the sympathetic nervous system, the branch responsible for fight or flight, the system that prepares the body for physical emergency, elevating heart rate, redirecting blood flow, sharpening attention, triggering the same hair-standing response that, in our furry ancestors, made them look larger to predators. Music is activating this system. Abstract patterned sound is being processed by the same neural machinery that responds to danger. Not everyone experiences this. Research consistently finds that roughly half to two-thirds of people report musical frisson. It's not universal. And the strongest personality predictor of who experiences it is openness to experience, a trait associated with aesthetic sensitivity, curiosity, and the tendency to engage deeply with ideas and art. Brain imaging studies show that people high in openness to experience tend to have stronger connectivity between the auditory cortex and regions involved in emotional processing, particularly the default mode network. Their auditory processing is more tightly linked to emotional and associative processing. The sound arrives and immediately triggers richer, more connected downstream processing. The architecture of their brain is more likely to produce the cross-system activation that generates frisson. Here's what should disturb you about this. The autonomic nervous system doesn't normally respond to abstract cognitive content. It responds to physical threat, physical sensation, survival-relevant stimuli in the environment. That it fires in response to a particular chord change, a particular melodic peak, a dynamic shift in a piece of music, this suggests either that music is reaching deep into acoustic patterns associated with threat or significance, or that expectation violation itself, the model being wrong, is inherently alarming to the nervous system at a level below conscious awareness. The brain is treating a wrong prediction as a mild emergency and rewarding itself for navigating it. There are specific musical features that reliably produce chills across many listeners. Researchers have catalogued them, and they're consistent enough to be interesting. A sudden increase in volume, or a sudden decrease, particularly after a period of sustained intensity. A new voice or instrument entering after a sparse, quiet passage. A harmonic movement to an unexpected chord, a borrowed chord from a parallel key, a modal shift that doesn't follow the established logic of the piece. A melody reaching unexpectedly high, a singer pushing to a note that feels beyond the ordinary range of the phrase. A moment of rhythmic displacement at a point of harmonic tension. In information theoretic terms, these are all moments of high surprise, events the predictive model assigned low probability. The model was wrong, significantly wrong, and the wrongness, in the right context, generates reward. This is measurable. Researchers have analyzed musical scores using information theory, computing the statistical surprise of each moment given what preceded it, and shown that the highest surprise moments correlate with the moments listeners report chills. The chill potential of music can be quantified mathematically, but, and this is the limit that matters for honesty, the same chord progression can produce chills in one listener in one moment and nothing in another listener, or in the same listener at a different moment. Context modulates the response. Personal memory modulates it. Emotional state modulates it. The mathematical structure of the sound is necessary but not sufficient. The listener's state is part of the equation, and that state is not captured by any analysis of the score alone. Now I want to say something that I think is the most important part of all of this. We can describe the mechanism of musical chills with reasonable precision. Prediction violation, dopamine release in reward circuitry, sympathetic nervous system activation, personality-mediated variation in brain connectivity, mathematical information surprise in the acoustic structure. What we cannot explain at all is why any of this is accompanied by subjective experience, why prediction violation feels like anything, why dopamine release is experienced as pleasure rather than simply occurring as a neurochemical event, why piloerection arrives wrapped in something that, to the person experiencing it, seems like brief contact with something that matters enormously. This is the hard problem of consciousness applied to music. And for musical chills, the gap between mechanism and experience feels unusually sharp, because the experience is unusually intense relative to what's causing it. A pressure wave in air, a shift in a chord, and something that many people describe as one of the most profound experiences available to them. Dirac believed that mathematical beauty was a reliable signal pointing toward physical truth. He trusted the feeling of elegance in an equation, the sense that the mathematics was doing something right, as a guide to whether the physics was correct. It wasn't superstition. It was a hard-won empirical observation that the theories which turned out to be true tended to be the ones that were mathematically beautiful. What does it mean that humans have a physiological response, measurable, reproducible, neurochemically specific, to mathematical structure in sound? Perhaps beauty is not a human projection onto an indifferent world. Perhaps the capacity for aesthetic response, for reacting to pattern, to resolved expectation, to the structural elegance of harmonic progression, is something that evolved alongside the same cognitive machinery that builds models of the world. The brain that predicts and updates is the same brain that finds prediction violation and resolution beautiful. And the chill is what happens when the model meets something it didn't fully anticipate, but recognizes the instant it arrives as exactly right. The air pressure waves don't care about your nervous system, but your nervous system was built over millions of years to care about patterns. And music, the deliberate, organized, expectation-manipulating pattern, found the exact door. What it found there, on the other side of that door, is the question we don't know how to answer yet. The mechanism we have, the experience, what it's like to have it and why, that's still waiting.